So in this video I'll discuss how one can get a motion diagram from x of t. So if you have an algebraic expression, x of t equals, for example, 2 minus 5t plus t squared, we can find the instantaneous velocity by taking the time derivative of x of t. And so if we do that, time derivative of 2 of 0 is 0. Time derivative of minus 5t is minus 5. Time derivative of t squared is 2t. And then one more derivative of v of t will give us the acceleration. And so the time derivative of v of t would be the time derivative of minus 5, that's 0, plus 2t is 2. And so reading backwards here, the acceleration is meters per second, 2 meters per second. The instantaneous velocity is minus 5 plus 2t, units are meters per second, and the x of t is the originally given expression. So a couple of things we can do right away. We can take the x of t expression and plot it here, and so I've done a hand plot. Horizontal axis is time. 1, 2, 3, 4, 5 seconds are plotted on the horizontal axis, and then the vertical axis now is x, horizontal position, in other words, is plotted on the vertical axis in this case. So you can see that the object is moving in the negative direction up until time 2.5, and this is a turning point, and then at that turning point it then begins to move in the positive direction. The v versus t curve shows the same kind of thing. So the velocity is negative from minus 5 to 2.5. That's easy to see in the v of t expression. And then for times greater than 2.5 seconds, the velocity is positive. In other words, the usual interpretation is that the object is moving to the right for greater than 2.5, and it's moving to the left for times between 0 and 2.5 seconds, not including 2.5 seconds. And then finally, the a versus t plot is shown here. It's very simple. It's simply a flat line, a meters per second. So in this particular case, this is a constant acceleration case, as you can see from the last expression. So if the acceleration is constant, the velocity is linear, and the position is quadratic. It's good to remember. Over here, I've organized the data in terms of tables. And the first column is time in seconds from 0 through 5, and then I've used the velocity either well, directly from this equation, but I've put the numbers in the table here, and I've used the instantaneous velocity to calculate the average velocity. And so, for example, from 0 to 1, the average velocity is the average of minus 5 and minus 3, which is minus 4, and then from 1 to 2, the average velocity is minus 2. From 2 to 3, it's 0. That interval includes the turning point. From 3 to 4, it's 2, and from 4 to 5, it's 4. And it's the average velocity, not the instantaneous velocity, that we want to construct the motion diagram. And since the average velocity is minus 4, minus 2, 0, 2, and 4, it means that the delta x is the same if I take delta t's of 1. And so based on this table, here's the motion diagram. From 0 to 1, the displacement is to the left a distance of 4. That's consistent with this minus 4 displacement. Then from 1 to 2, there's a displacement of minus 2, right off the table here. From 2 to 3, there is no overall motion. From 3 to 4, there is a displacement of plus 2, and from 4 to 5, there's a displacement of plus 4. So here's one for you. Let's say we had a position versus time of -3 plus 2t minus t squared. What then would the v of t be? What would the a of t be? And make a sketch of the motion diagram in that case.